And so our next clue was, all right, we didn't know much about InnoDB buffering, which I would imagine you don't know much about it either. And so that was the exact same position we were in. All we know is this thing called the iBuff. We have no clue about it. There's not that much written about it. So we had to dig in and find out. So what's InnoDB first? InnoDB is the default storage engine for MySQL. So storage engine is just the underlying software that's used to do your reads, your creates, your updates, and deletes from the data in your database.
So one quick thing. It sounds like you've used MySQL for some time.
A little bit.
Remember what the default used to be for the storage?
MyISM.
Which is problematic because it doesn't allow all the nice properties of databases. It's basically a fancy Excel file. So, anyway.
Yeah, so MyISM didn't have this iBuff, this data structure that we're going to look into. MyISM didn't have it. So InnoDB has it, and it's actually really special and cool. There was just a bug. So, and it allows for those ACID transactions that we talked about in class. So this is InnoDB at a high level on memory and then on disk. So I'm just going to kind of go through some specific data structures in InnoDB that are really relevant and interesting for this project. So specifically, we're going to look at the buffer pool in memory and the change buffer. Remember, that's the iBuff in memory. And then their corresponding files on disk. So on disk, you have the IBD files. Those are the actual data files, so your table data and your indexes data. And then the change buffer on disk where it's persistently stored. So in memory, here's the buffer pool. This stores cached pages for data and indexes. So that gives you really fast reads and writes. If you've performed a query once, now it's cached in memory. You perform it a second time, it's very fast. The storage unit is one page, and the pool is managed as a list using the least recently used algorithm. And then here's its corresponding files on disk, those IBD files, and those are the persistent pages that are stored on disk. So you have the clustered pages. Those are your data and your primary indexes that we talked about, and then secondary indexes, which are those extra keys that the professor was talking about. And then our change buffer is just going to store a record of changes that you need to make to secondary index trees on disk. So it's not actually making those changes, it's just storing a record. We need to make these changes later. We need to make these changes later. And this is a cached B+ tree that fits entirely into memory. And there it is on disk, just for persistent storage. All right, so what happens with the incoming query? I'll show you how InnoDB manages this at a little bit of a lower level. So let's take a very simple query, select star from my table. So the first thing that InnoDB will do is it will look for the page, that page that the query is corresponding to in the buffer pool, in the cache memory. If it finds that page, excellent, let's deliver it to the request. If it doesn't find that page in memory, it's going to look for the files on disk. Remember, looking on disk is going to be a little slower. If it finds that page on disk, it's going to copy it into the buffer pool, and then from the buffer pool, deliver it to the request. So something that you'll see is that an incoming request always goes to the buffer pool first, checks in memory before it goes on disk. Now, a little bit more complex query. Let's do an update. Update my table, set this column equal to 0. This column doesn't have a secondary index on it. Look for the page in the buffer pool. If we find the page, we're going to modify the page, so update that data, and then the page is going to have a tag that says, okay, this page is dirty. That means we need to take the changes on this page and put them on disk.
Explain what you mean by dirty.
Dirty means it has changes that are in memory, but those changes are not recorded on disk. So for instance, let's say now I've made these changes, I want to move this table to our production servers so users and researchers and journalists can see this fresh data that I have. It's not currently in the files on disk. So there's a tag in memory that says, all right, this data is dirty. We're going to have to flush it to disk before that persistent storage is created. All right, and if found, copy it to the buffer pool as before. Once it's in there, modify the page and mark it dirty. All right, so what happens to dirty pages? High level, executing DML, that's that data modification language that the professors talked about. That's inserts, updates, and deletes. That's when you change the data. So you bring the page into the buffer pool. You edit the page and mark it dirty. You write a record of it to the log. And then you flush the changes to disk at your convenience or at the system's convenience. Any questions so far? Okay, so full architecture, this is back to that higher level overview with more data structures. You see that log buffer at the bottom in memory and the log files on disk? It's going to use logging just to optimize I/O and recover data. That's what InnoDB does, helps you recover data in case of a crash. So if all of a sudden your system crashes, you have these log files that have a record of some changes that you've made. So first, after you change that data and mark it dirty, a record's going to be written in the log buffer. It'll immediately be written to the log file. And then later, a background thread is going to go through and actually take those dirty pages and merge them to disk. Does that make sense? And just like the change buffer, the log has a copy in memory on a disk for quick writes and persistent storage. All right, so now let's look at what happens when an update occurs with a secondary index. And the change buffer specifically changes that are buffered to secondary index pages. So this is really what we're interested in. Update my table, set is indexed column equal to 1, where ID is less than 11. And this column has a non-unique secondary index, and these are the kind of changes that are buffered in the change buffer.
I have a question.
Yeah.
On the previous slide, when a page is made dirty, what if the user makes another change that undoes the first change and now it's logically clean?
Good question. So first, all requests go through the buffer pool. So I think my understanding is if it goes into and finds the page, it'll find the page in memory, so that's the page it's looking for, but it sees this tag that says, hey, this is dirty. I think my understanding is that it's going to flush that change first and re-pull it back in.
So it's going to do the whole thing anyway.
I could see that being more sufficient. It's a good question, something to dig into.
So,
Yes?
so if somebody actually accesses that page from another computer, will they just see the old version if it didn't go through until to disk yet?
Right, so if they're, from another computer on the same server, they're still going to, all requests are going to go through the buffer pool first.
Oh,
so their request is also going to hit the buffer pool before it checks on disk.
Okay.
So they'll see the dirty page?
They'll see the dirty page cached.
Okay. Okay.
Yep, all requests go through the buffer pool. It's really important. All right, so as before, we're going to get that page, we're going to modify it and mark it dirty. So we've just changed the data to a column that also has a secondary index on it. And what we know, we changed the data, but we have this index tree, so what do we need to do to the index tree? We need to update the index tree, right? So now we have to modify that secondary index page too, and it's stored in a different kind of page. So secondary retrieval is going to require random I/O, which we know is more expensive than sequential I/O. So InnoDB is really special. It's created this data structure called the change buffer in order to limit random I/O so that we have faster systems. All right, so it's going to use the change buffer to defer this cost. So if that index page, now that it wants to modify, is already in the buffer pool, let's modify it and mark it dirty. But if it's not already in the buffer pool, instead of immediately reading from disk, let's record that change to limit random I/O. And that's where we're going to use the change buffer. So the change buffer is this B+ tree. The key is the space ID, so that's the table that we're interested in, and the page number. So a change is recorded in the change buffer. It says, make this change to this index page. Make this change to this index page. Make this change to this index page. And that change buffer fills up with records of changes that need to be made. So how do we merge these changes back on disk? They occur in two ways, on demand or periodic merge. So on demand occurs when that index page is requested. So let's say I just run flush tables for export on a specific table. I'm like, all right, I want to push this table to production. I need to merge all the changes. So I'm going to run flush tables for export, specific table name, and that's an on-demand merge. So it says, okay, great, we have an on-demand merge. Let's get those IBD files, make those changes. And once it's brought into the buffer pool, it's modified, marked dirty, and ready for a flush, just like data. And then periodic merge is just the background thread. So I haven't made a specific change, but the background thread is constantly running over the change buffer and saying, okay, based on what my I/O is at this time, I should make a few merges back to disk. And they occur about every 1 second. And if your system is very active, you're going to have more idle merging, right, to preserve resources. And if your system's really idle, you're going to have more active merging. So my system was idle, so we just inserted millions of records, but immediately we had very active merging and just merged those changes back because I didn't have a lot going on in my system. If I had lots of data transformations and I was running lots of inserts and updates and deletes all at the same time, it might say, okay, let's just merge a little bit at a time to preserve resources. All right, so that means we should see this high iBuff size when heavy DML is running on the system. And witnessing a high iBuff size with heavy DML, I'm not going to go back to the demo because it's a little funny to switch over from the two things. But we saw earlier, right? So what we did was we started inserting those records, and the iBuff size changed from 1 to 76 in an instant, right? It started filling up with pages. And that's what we see, and that's what we were seeing when we had these system lock problems. The issue, though, is we weren't seeing just 76. We were seeing thousands and thousands and thousands of pages in the iBuff, and that would take a long time to flush back. All right, so now we kind of dug into InnoDB buffering. We know a little bit more about InnoDB buffering. So that led us to a hypothesis about what's happening with flush tables for export and that system lock. So we said, okay, when heavy DML, when we have this system where we're doing a lot of data transformation, a lot of updating and freshness of data, then the system's loaded, so merges are idle. So we predicted that the iBuff is being added to faster than it's being removed from. And because that purge thread, remember that background thread, because potentially it's unable to merge all of those changes because it's being added to faster than removed from, then we hypothesized that that flush tables for export system lock was unable to be released because it couldn't actually merge that table yet, that data. So that was our hypothesis. And this is kind of where we went from there, and we'll figure out if we were right or not. So in order to test our hypothesis, now we know about InnoDB buffering, the iBuff. We need to look at the other component, flush tables for export. So we dove into MySQL source code to find out more. And if you have a Mac, for instance, you can use Xcode. You can set breakpoints in MySQL, and then you can run processes and kind of step through those breakpoints to see where you hit. And where we hit is a function called flush tables for export. So flush tables for export has 5 big steps, but we're really only interested in one step. And this is acquiring a shared no-write lock on the table, because that's our system lock. So we want to see what's happening, where are we getting stuck in here when we run flush tables for export. Any questions so far?
Yeah, one thing, we're going to talk about locking and all that when we get to transactions. So some of this is great prep work. In fact, if you want to do my transaction lecture, that'd be great. Yeah.
Cool. All right, so I hope you guys can see this. In flush tables for export, we're going to acquire this shared no-write lock on the table. And there's this function called open and lock tables. So I said, okay, great. Let's go into open and lock tables. So now we're in open lock tables. We see this function called lock tables. All right, cool. Let's go into lock tables. And then MySQL lock tables. We're like, okay. And then lock external. And then external lock, row quiz, table start. And then finally, iBuff contract in background. That's our little friendly iBuff. So we're thinking, okay, something's happening in there. All right, so here's iBuff contract in background. It's going to take 2 parameters, table ID, so which table are you going to merge those changes from, and then a Boolean flag. Are you going to do a full contract? Are you going to merge all of the changes? Or are you going to only merge a certain percentage based on I/O, disk I/O? So now let's dive into the function. We get in there and we see an interesting while loop. And as computer scientists, that usually piques our interest. Maybe there's something strange happening here. So that's where we started. It's while some pages is less than n pages. Some pages is the number of pages that have been merged from the iBuff to the buffer pool so far. So let's say your table has 20 pages, and we've merged 5 pages so far. So we have 15 to go, right? N pages is the number of pages to be merged total. So we have 20 pages total to be merged, and we've merged 5 pages so far. So we're not going to exit this loop until we've merged all the pages. So how is n pages set? Remember, n pages is the number merged so far. Either the caller requests a full batch. I'm the caller, right? I want to move this table from one server to another. I'm going to request a full batch by running flush tables, specific table name for export. Or 5% of I/O capacity, which is that background thread, right? That background thread is just going to merge some of the pages in the iBuff generally. And it ends up being 100% of I/O capacity is 200 at a time or 10 at a time. All right, so there's 2 ways to exit this loop. If some pages is equal to or greater than n pages, right, if we've merged all the pages, or if n bytes is 0. So let's look at that. This line, iBuff merge, this actually modifies both of those variables. So n bytes is returned from ibuff merge, and n page 2 is passed by reference in that function. In C++, you can pass a variable by reference. You change it in the underlying function and in the called function, and then you don't actually return that variable. It's just changed immediately. So n bytes is going to satisfy one exit condition. If n bytes is 0, then return. So that's saying, hey, if there are no pages to be merged, like let's say that ibuff is empty, there's clearly no pages to be merged, let's just return, right? And n page 2 is going to increment the check for the other condition. So as we increment n page 2, then it increments that check, and then we can finally get some pages equal to or greater than n pages. Does that make sense? Basically, we're checking to see, have we merged all the pages so far? If we have, cool, exit the loop. If we haven't, stay in the loop. And every time it goes through, it's going to merge some number of pages each time. All right, so let's look into ibuff merge. We see that volume is returned by ibuff merge. So great, that's that variable that we want to change. And volume is set by ibuff merge space. Same kind of idea, we have to keep digging. Now looking into, and you see n page 2, that's passed by reference, it's initially set to 0. So it says so far, it's defaulted to 0. All right, so let's look at ibuff merge space. That gets our return variable. Looking at ibuff merge space, it returns some sizes down at the bottom, but we also see that it is, some sizes is incremented by 1 before returning. So ibuff get merged pages is going to set some sizes. It's incremented by 1, and then it's returned. So that's still that variable that we need to exit our while loop. So now let's look at ibuff get merged pages. ibuff get merged pages returns a lower limit on the number of pages to be merged. So my table has 20 pages to be merged. It says in this round, let's say, for instance, let's merge 5 of them, and then we'll go back into the loop and do it again. But question is, remember our app table? How many pages did it have in the change buffer? 0. So the question is, what happens if the table has no changes to be merged? So let's go with that idea, because we simulated it in our test environment. We saw this crazy case where this table that had absolutely 0 pages to be merged was hanging for hours and hours. So we want to look specifically in the source code at that condition, where a table has no changes to be merged. All right, if the table does not have any changes recorded in the change buffer, then we're going to return 0. ibuff returns the lower limit on the number of pages, 0, so it's going to return 0. Excellent, it returns 0 to some sizes in ibuff merge space. Oh, but some sizes is incremented here. So it was 0. Remember, this number is going to be n bytes. If n bytes equals 0, we get out of the loop. It was 0, but now we're going to increment it to 1. So it's incremented to 1, and now some sizes is returned. Which means that now ibuff merge space is going to return 1 to volume in ibuff merge. There it is. And volume equals 1 is returned to the while loop. And you can see n page 2 that was passed by reference, it was defaulted to 0, and it's still at 0. So after ibuff merge returns 1 to n bytes in the while loop, the exit condition n bytes equals 0 will not be satisfied. And no pages were merged, so n page 2 is still 0. So some pages, the number of pages which have been merged will not increase past 0. And some pages will still remain less than n pages. So neither exit condition will be satisfied. And this is where we're stuck in this loop until we make some change, like we kill all of our processes or we restart MySQL, for instance. And that's one infinite loop. So if there are no records in the change buffer, so the change buffer is empty, for that table being called, does this mean that the loop will run forever? Well, we're not seeing this happen on our system every day. We're seeing it sometimes, maybe once a week, maybe once a month, maybe twice a week, sometimes maybe 3 times a week if we are having a really busy data processing week. So there is a way out. In ibuff merge, there's a check to see if the ibuff is empty. So if the ibuff is empty, we're going to just return 0 to n bytes, and that exit condition will be met. So it's not going to increment it. That's in a following function. So ibuff is empty, return 0. Great, we're going to hit this exit condition, n bytes is 0. But what did we just see when I was inserting 50 million records? So I'm inserting 50 million records. What happens to the iBuff?
Increases.
It increases in size. So let's say I'm inserting 50 million records to my table. Let's say another data engineer or a product manager is updating data. So now they're updating 20 million records. Let's say somebody else is deleting a bunch of data. So now we have this iBuff being slammed and it's not emptied. And maybe it's slammed all day because we're a data company and we process a lot of data. So maybe it's slammed all day and maybe it's slammed for a week. So now this iBuff isn't going to empty by itself. So we're going to stay stuck in this loop. So is our hypothesis correct? No. It was actually the opposite. So we thought, okay, the purge thread is so busy trying to merge all the changes. There's all these changes happening. It just can't get to the changes for that table. It can't get there. It can't empty it out. But it was actually that there are no changes to merge for that table. So we hit an edge case. And the edge case is specifically, iBuff is not empty. The size is greater than 1. And the table being flushed for export has no changes recorded in the change buffer. And you might be thinking, okay, you guys hit this case. It was causing these system locks that happened, for hours upon days. How come other people weren't hitting this case? We think it's because we're doing a lot of data processing. We're just pushing MySQL to its limit, and we're using it in ways that maybe other people aren't using it, or we're pushing a lot of data through to build the world's knowledge graph, and, we're testing the limits of MySQL. So that's kind of our hypothesis why other people haven't faced this. So how do we resolve this? First, we submitted a bug report to Oracle and Percona. We kind of had a bet that Percona wouldn't respond. And
Who's Percona? I missed that.
Percona is another MySQL. Percona is also open source, but then they have their proprietary support for MySQL.
Oh, okay.
Yeah. So we submitted a bug report to Oracle and Percona. We kind of thought maybe if anyone answers us, maybe Oracle will. That was just our guess. And then while we were waiting for them to respond, we had to create a fail-safe for our system because we have these production servers. It's unacceptable for them to go down or for our data to not be fresh for instance, Huffington Post or AOL or Yahoo or the AP. So InnoDB is customizable. That makes it really interesting for data engineers. We have this variable, InnoDB change buffer max size. It's dynamic. We can change it on the fly, and that'll just disable new inserts to the iBuff. So to disable new inserts, either set global change buffer max size to 0, limit the size, or turn off buffering and just set change buffering equal to none. And so what happens there, we're inserting all of this data. It's utilizing the iBuff. Maybe there are 50 pages in there. We turn it off. Those pages are still in there, but no new pages will get inserted. It'll start just doing random I/O and going to disk to write those changes immediately. So then that background thread will just merge the changes, and then the iBuff will be empty, and we'll hit the exit condition.
What's the downside to doing that?
Well, I'll show you.
Thank you.
Yeah, so this will prevent new additions to the iBuff, and the background thread will be able to merge remaining changes, and we'll see a release of that long-running system lock when InnoDB iBuff size equals 1, because we'll hit that condition, iBuff equals empty. But relying on manual intervention places unnecessary risk on our system, so we don't want to be woken up at 2 a.m. from an alert that's saying something's happening with our system and have to go in. That's not optimal. So we created a programmatic failsafe until the bug was officially resolved. So what we did in our data logistics process is we said every time we call flush tables for export, before we call it, let's disable the iBuff. If it's empty, it'll be empty and the flush will go through, and then we'll just re-enable it. If it's not empty, it'll take a little bit of time to merge those changes, but it's not going to cause a problem on our system. So you might be wondering, as the professor did, why don't we just disable the change buffer entirely? Change buffer is actually pretty powerful. So, sorry you might not be able to see this so well, but I just wrote some bash scripts for performance testing on insert time. So we have people that are doing a lot of big data. They're going to be really upset with me if I disable the change buffer entirely, and their previous data transformations went from taking an hour to 24 hours. So I had to test this out before I implemented that failsafe. So you can see in red, we have the first is 5 million row insert, then 10 million row insert, then 20 million row insert. In red on the left side is with the iBuff enabled. So this is the insert time. And then yellow on the right side is with the iBuff disabled. So it's about 3 times the insert time when you disable the iBuff. So it really is optimizing for our system. Really is important and a great feature of InnoDB. So disabling it entirely wasn't an option. What I did then was I tested that periodic insert. So we call a flush, we disable it, maybe 10 seconds, maybe 5 seconds, maybe a minute if it's filled with records. And here with this periodic disable, so you have fully enabled in red, 10-second disable in yellow, there's almost no difference, and then 60-second disable in green. That's an acceptable time hit for us to take in order to keep our system safe. So we went with this fail-safe until MySQL fixed the bug. So you might be wondering, did the bug get fixed?